Welcome to this explainer on hydrophobic interaction chromatography. I'm Dr. Chem, and I'm going to be your guide through this really fascinating analytical technique today. Look, whether you're scaling up a massive biomanufacturing process or you're just trying to isolate that one incredibly tricky enzyme in the lab, this technique, it's an absolute cornerstone of modern biotechnology.
So, let's kick things off by asking the million-dollar biomanufacturing question. How exactly do we clean up super delicate therapeutics, like monoclonal antibodies, without completely denaturing their natural folded structure? Because, a lot of traditional separation methods use these harsh organic solvents that just unfold and totally ruin the biological activity of these incredibly complex, fragile molecules. We really need a method that is gentle but still powerfully selective.
Here's our syllabus for today's masterclass. We'll start with a quick introduction to HIC, dive into the core principle, look at the system components and workflow, weigh the advantages and limitations, and finally, wrap up with some real-world applications.
All right, Section 1, let's get right into our introduction to HIC.
Hydrophobic Interaction Chromatography, or just HIC for short, is a liquid chromatography technique that separates biomolecules based purely on their surface hydrophobicity. Now, you can kind of think of HIC as essentially a milder, gentler form of reversed phase chromatography, but here's the catch. While reversed phase uses organic solvents that can easily destroy a protein, HIC exploits those hydrophobic regions on macromolecules to separate them right in aqueous solutions, meaning their biological activity stays perfectly intact.
Moving on to Section 2, let's unpack the actual principle of HIC.
Now, in most chromatography, you add a solvent or increase a gradient to elute your target off the column, right? Well, in HIC, we do something kind of crazy. We use a reverse salt gradient. This means our proteins actually bind to the stationary phase at extremely high salt concentrations, and then they elute, or, let go, at low salt concentrations. It is completely backwards to what you might expect at first, but the physical chemistry behind this is just brilliant.
This image right here perfectly illustrates that principle. Notice the water molecules. Usually they form this highly ordered shield around the hydrophobic patches of a protein. But when we pump in a really high concentration of salt, those salt ions interact so strongly with the bulk water that they literally steal the water away from the protein. Suddenly, that water is no longer available to act as a shield, and this forces those exposed hydrophobic patches to cluster together with the mildly hydrophobic ligands on the stationary phase. It's honestly a lot like a bunch of people crowding together under a tiny awning to escape a heavy rainstorm. So to really contrast these two states, that high salt concentration boosts the target-ligand interactions, effectively locking your protein right onto the column. Then, by slowly reducing that ionic strength, literally just washing the salt away, we weaken that grip. As water becomes available again to shield those hydrophobic patches, the molecules finally elute. And the cool part is, they elute strictly based on their specific degree of surface hydrophobicity. So your least hydrophobic proteins, they wash off first. Meanwhile, the highly hydrophobic ones hold on for dear life until that salt concentration drops to nearly zero.
Of course, the absolutely crucial point here is choosing the right salt. We can't just dump in any old table salt, right? We typically rely on highly lyotropic salts, like ammonium sulfate. If you look at the Hofmeister series here, they sit way over on the far left. These lyotropic or salting out ions have a massive capacity to promote those hydrophobic interactions without actually precipitating your protein out of the solution entirely. Ammonium sulfate is pretty much the absolute gold standard for striking that perfect balance.
Okay, moving right along to Section 3, System Components and Workflow.
So what's actually inside the chromatography column? Well, we have our mildly hydrophobic stationary phase. Basically, the base resin is coupled with ligands, which you can see mapped out here from least to most hydrophobic. Up at the top, we've got our hydrophilic ethers, then we move down to moderately hydrophobic phenyl groups, and all the way down to highly hydrophobic butyl or octyl chains. And your choice of ligand is super important because it dictates exactly how much salt you're going to need. For example, if you go with a weakly hydrophobic ligand, like an ether, you are going to need a much higher starting salt concentration just to force that protein to bind.
Now, the actual day-to-day workflow in the lab follows 5 really distinct steps. First up, we equilibrate the column with our high salt binding buffer. Step 2, we load in our sample, which is also dissolved in high salt, and let those hydrophobic proteins bind. Third, we wash away any of those unbound impurities. Fourth, we execute that magical decreasing salt gradient we talked about, which elutes our targets one by one. And finally, step 5, we use our fraction collector to gather the samples and analyze them.
We're usually using a UV detector, maybe some SDS page, or protein activity assays, just to measure the concentration and purity as it all leaves the column.
When you map this whole workflow out over time, it reveals this really fascinating dynamic. Check out that red line. That's representing our salt concentration, or conductivity. And as you can see, it drops at this nice, steady, linear slope during the gradient elution phase. But at the exact same time, look at the blue line. That's our UV absorbance, showing us the proteins themselves. Literally, as the salt drops, you can just watch those tightly bound molecules finally let go, popping up as these beautiful, distinct, highly resolved peaks.
All right, Section 4. Let's talk about the advantages and limitations of HIC.
On the plus side, HIC is totally championed for its gentle, non-denaturing conditions. It preserves protein activity, it offers incredibly high recovery rates, and honestly, it scales beautifully for industrial manufacturing. And because it operates orthogonally to other methods, like ion exchange, it is just the perfect complement in a broader purification pipeline. But we definitely have to acknowledge the hurdles here. The chromatography media itself can be pretty costly. Plus, it really doesn't work all that well for molecules with very low surface hydrophobicity. And honestly, the biggest thing? There is a massive amount of salt optimization required. If you overshoot that salt concentration even a bit, your precious protein sample is going to simply precipitate right out of the solution before it even enters the column.
For example, let's say you run into a troubleshooting nightmare where your target protein, like that little shaded peak you see right there, elutes way too early, with just terrible resolution from all the other impurities. What does that mean? Well, it means you've got a weak interaction, so you've got to go back to the drawing board. You either need to bump up your starting salt concentration, maybe choose a salt with a higher salting out strength from that Hofmeister series, or just swap your entire column for one with a more hydrophobic ligand, like upgrading from an ether to a butyl phase.
And that brings us to Section 5, Real-World Applications. So why does all this matter outside the classroom? Well, because HPLC separates biomolecules while strictly maintaining their native structure, it has become an absolute cornerstone in biotechnology and biopharmaceutical manufacturing. It's heavily utilized as this vital polishing step in downstream processing. Basically, once a sample has been roughly cleaned up by other methods, HPLC steps in to do the heavy lifting, purifying life-saving therapeutics, separating out product aggregates, and isolating incredibly complex molecules like monoclonal antibodies, enzymes, recombinant proteins, vaccines, and even plasma proteins, all on a massive industrial scale.
Just take a look at this incredibly sharp separation of a monoclonal antibody variant on an adjuvant column. This shows exactly why the industry relies so heavily on this technique. Notice how that tiny little excipient peak is just perfectly separated from the massive, pure MIB peak? To meet the insanely strict regulatory purity profiles required by agencies like the FDA, ensuring absolutely no aggregates or host cell proteins are left in the final drug, HIC isn't just nice to have, it is literally an indispensable tool.
As we wrap up this masterclass, I want to leave you with this thought. The biological medicines we are designing today, they are becoming exponentially more complex. So as we push the boundaries of medicine, how will fundamental techniques like hydrophobic interaction chromatography have to evolve to keep our most vital, life-saving proteins safe, active, and perfectly pure? It's something to think about. Thank you so much for joining me on this explainer, and keep exploring the incredible world of separations.